This second precast on bones and skeletal tissue continues with a conversation on bone development. Now, an important aspect of thinking about bone tissue is the way bones develop. They are capable of substantial remodeling, and it involves a process that essentially builds on the way that bones first develop embryologically or embryonically. There are two aspects of this, osteogenesis and ossification. So the osteogenesis is the development of the bone cells, and ossification is the way that the hydroxyapatite calcium phosphates are added to the matrix of the bone that gives the bone its hardness and strength. So the process that we're talking about then is involved in the formation of the embryonic skeleton. It's a process that continues into early adulthood, and we're talking about extending then into the early 20s. And then it's a process that is revisited time and again over the course of one's life to remodel a bone in response to the way our bones are used, the kinds of stresses that we place on them and the kinds of movements, the kind of muscle contraction that pulls on the bones will in fact cause changes in the bone in response to it, in adjustment to those kinds of stresses. And of course there's also the ability to repair injured or broken bones as well that many of us are aware of from various kinds of injuries. So there are basically two kinds of processes for bone development. One that we call intramembranous, sometimes known as dermal development, and the other is endochondral. So let's talk about each of these in turn. Intramembranous ossification starts with mesenchyme, which is a kind of embryonic connective tissue. And some mesenchyme cells begin to cluster. They differentiate into osteoblasts, which, as I mentioned earlier, are the kinds of cells that create new bone cells and ultimately osteocytes. They are also capable of making osteoid, and so they secrete the osteoid. And it begins to accumulate in a matrix surrounding these cells, and we begin to see it as sort of a core from which the rest of the bone will develop, and that's called an ossification center. Now notice already that part of the osteoid that's emerging from this are collagen fibers. Collagen fibers are part of the osteoid, they are part of the matrix, they are part of what gives bone its strength, in addition to the presence of the mineral salts, the calcium phosphates. Eventually, the osteoblasts turn into osteocytes, especially once they've been trapped in the osteoids for a while. So the ones that are still dividing, that are still producing the osteoid, remain on the outer edges of the ossification center. And so here you have the osteoids. They begin to be trapped in the part of the matrix that now becomes ossified or calcified. And then eventually you have the accumulation of osteoid that's laid down around blood vessels and embryonic blood vessels. And now, instead of having lamellae of the sort that you see in, especially in compact bone, you see the development of these spaces and trabeculae that lie, that essentially separate the spaces. And of course, what we're seeing then is the formation of spongy bone in this particular case. And then ultimately, the compact bone does begin to develop. It doesn't have, typically, at least in this kind of bone, for example, this would be typical of the flat bone of the skull. You would have some compact bone, but it would have limited Haversian canals or osteons. But certainly what you would have on the outer surface, right under the periosteum, would be the location of osteoblasts, which are capable of substantial remodeling. Now, endochondral ossification is the kind of development that's more characteristic of long bones. And in this particular case, instead of the bone developing from mesenchyme connective tissue, especially the kind that's associated with flatter bones associated with skin, for example, or dermis. That's one of the reasons they're called dermal bones. In this particular case, you begin with hyaline cartilage, of all things. The cartilage essentially sets down a model for how the bone will develop. And it's hyaline cartilage, and the bone begins with the formation of essentially a collar around the outside of this cartilage. And within, you also have the development or creation of a primary ossification center. And where that ossification center occurs, you will then begin to see a deterioration of the cartilage. Ultimately, as you go through this process, you will eventually get the creation of a long bone. Let's take a little bit closer look at the sequence then in the subsequent slides. So like I said, you begin with the primary ossification center that occurs within the hyaline cartilage model. The cartilage begins to deteriorate as the bone develops. So now you have spongy bone within, you have the compact bone forming outside, and other ossification centers develop in the epiphyses, in addition to in the diaphysis. Ultimately, a medullary cavity is created. And by the way, in this process, what we're seeing is not the conversion of the cartilage into bone, it's simply the replacement of the cartilage. As it says, we've talked about deterioration of the cartilage with bone forming in its place. And then ultimately, you have a substantial amount of bone tissue. There's actually articular cartilage that remains at the joints. But until early adulthood, in other words, early 20s, there will still remain essentially a plate of cartilage that serves as a site for continued ossification development. This is called an epiphyseal plate, and this is as we'll see, this is a site for continued growth of the bone in either direction. Here's another epiphyseal plate. And this is part of the additional final stage of growth that occurs in this early adulthood phase. This is simply an illustration using a particular stain that identifies the primary ossification centers in a 12-week-old fetus, and it's quite remarkable to be able to see the basic structure of the human skeleton visible this early in development. So we're talking about 3 months of age, very clear humerus, radius ulna, femur, tibia and fibula, at least part of the pelvic bone, the ilium, ribs, very distinct ribs. Notice that the cranial bones are established, but there are still very large joints that sit between them called sutures. Ultimately, the bones will fuse together, of course, but that doesn't happen until after birth. Now, this is just an illustration of the way that we can compare the process of growth and remodeling in long bones. So as I said, there's an epiphyseal plate. The growth occurs at that plate, and it will grow essentially outward in this way. In other words, additional cells are added here. The cartilage is replaced by bone, so there's this outward growth. But to establish the continuity of the diaphysis at this position in the medullary cavity and so on, where there's growth here, there is resorption here, and there's a resorption here, so that the bone will expand here to go from here to there, and yet there would then be resorption to go from here to there. So this is the kind of thing that happens in growth, but there's also going to be remodeling as well. That is a part of this process. Now, in this process then, there are two kinds of cells that we've mentioned in passing, osteoblasts and osteoclasts, that drive the different aspects. That the osteoblasts are engaged in deposition, the creation of the osteoid of the matrix. The osteoclasts are engaged in resorption. So osteoblasts for deposition, osteoclasts are involved in deposition. And this is the kind of thing that tends to happen in the outer, just deep to the outer and inner membranes, the periosteum and the endosteum. Now, what controls this? There are actually hormones that do. The primary, there's one particular primary hormone that we'll talk about, parathyroid hormone, and it is particularly involved in regulating calcium homeostasis, to regulate the levels of calcium within the blood as well as the levels of deposition within the bone. And then there are also forces, mechanical, gravitational forces that act on the skeleton that can also drive the remodeling. So the primary hormone that's involved in this is parathyroid hormone. There is a second hormone, not to jump ahead too quickly, the parathyroid hormone comes from the parathyroid glands, which lie just behind, just posterior to the thyroid gland that wraps around the trachea and the larynx, right about there. We're looking at the posterior aspect of the thyroid and the parathyroid. There is a second hormone called calcitonin that is secreted by the thyroid gland that used to be thought to have a particular role in calcium homeostasis, and in fact, in opposition to the effects of parathyroid hormone, it's now believed that it has a much more minor role. So even though the diagram illustrates how it might be involved in helping to counteract the effects of parathyroid hormone, sort of like what you see the respective roles of insulin and glucagon in regulating blood glucose. The parathyroid hormone has a much more important role. So to the extent that calcitonin is involved at all, it could respond to rising blood calcium levels and helps to stimulate the deposition of bone. There is some of that effect. It just may not be enough to truly participate effectively in regulating homeostasis in the way that's illustrated here. On the other hand, when there is falling blood calcium levels, that certainly does stimulate the parathyroid glands to release parathyroid hormone, which in turn stimulates the osteoclasts to break down the matrix, release the inorganic calcium, and that released into the blood will restore the levels of blood calcium to their normal levels. Now, as far as mechanical forces influencing the maintenance of bone, something called something called Wolff's law is a variation of the use it or lose it mantra that essentially bones respond to the way that they are used and can be remodeled in very specific ways, especially at younger ages, and it actually helps to explain how different kinds of attachment points can in fact be expanded or strengthened as a result of different kinds of exercise. One of the things that we find that's very interesting about bone in the way that it responds to stress is simply the way that they are structured. That, for example, looking at the femur, here's the head of the femur that would attach within the pelvis. It's angled in such a way that the forces of compression that would occur as a result of the weight of the body bearing down on the head of the femur would be balanced almost precisely by the tension of pulling apart the outer part of the diaphysis of the femur, such that the center of the bone is essentially a place where there is very little stress at all. It is negated. So there's compression on the inner surfaces, pulling apart or tension on the outer part, and that means there's no stress in the middle. That's the kind of thing that can account for the fact that that places this point of no stress right in the middle of the bone. In fact, this is a place then where you can actually stand, the body can withstand not having any bone tissue here at all. This is in fact where you would find the medullary cavity. Another thing that can happen is that, as we've touched on, that there is an expansion, there can be an expansion of bone at particular attachment points for muscle and in certain kinds of movements and exercise. Illustrated here would be the forearm bones. As a result of playing tennis, for example, there can be an expansion of the diameter of the humerus or of the forearm bones in a way that makes that bone larger in the arm that's used to hold the tennis racket compared to the other one. Now, just to touch briefly on what happens in a fracture, it's a very important example of the process of growth and remodeling, that bone tissue can reconnect itself across a break of this sort. And for me, the take-home message is the importance of blood supply, that the bone is a living tissue, and what is absolutely necessary to occur in this process of regrowth is the ability of the blood vessels to penetrate across the cut to be able to supply the needed additional calcium and phosphate and to deliver the materials needed to make more collagen fibers and the other aspects of the osteoid to ultimately be able to provide this healing that can ultimately and quite reliably occur in most people who have these kinds of breaks, given enough time for rest and the absence of stress on that area. It's quite successful. Now, finally, I just want to touch on what can happen when you have imbalance in the various aspects of bone tissue. It results in particularly two kinds of pathologies. One is where there is a deficiency in calcium or uh, vitamin D, which can affect and cause a deficiency in calcium because it affects the way that calcium is absorbed out of the diet. Um, and the result is that you have osteoid, but osteoid that's not ossified, filled and hardened with calcium phosphate. And this is what characterizes the two diseases, osteomalacia and rickets. Osteomalacia is what you would see in adults, rickets in children. And it essentially provides, or produces rather, bones that are flexible rather than hard. So the result is a skeleton that's much less able to provide proper support and protection. Because it's more like cartilage alone without the calcium ossification. On the other hand, osteoporosis, which you may have heard of, more likely to have heard of, characterizing older adults, particularly older women, is a result of the resorption of the bone tissue that exceeds deposition. So the bone tissue becomes more and more porous as a result. So there's still calcium. There's ossified osteoid, but because it has less and less of the matrix, of this part of matrix, the bone becomes very brittle. And so this is the kind of circumstance that leads to fractures. And this is what it looks like. And I think it doesn't take much imagination to think that this kind of tissue is illustrated from osteoporotic bone is more likely to break compared to normal bone. So this is the end of the second precast on bone and skeletal tissue, focusing on bone development.